think. Okay, let's go. Almost like coughing and sneezing. I guess I'm not the only one that this weather doesn't agree with. I'm from a tropical country though, so I have an excuse. Like, what are you? Is everyone from here?
No.
Is anyone from somewhere tropical, like it's hot all the time? Okay, you guys have excuses. The rest of you, I don't know.
Florida.
Yeah. Like, I'm used to it being like 85 degrees like all the time. So it's not agreeing with me. I already got the flu and I think I'm getting another cold again. So it's like, last time, let's pick up where we did last time. We'll do a little bit of review just by going over this problem. So we actually already did this, but I want to just go over it to like jump your memories, and then we'll pick up with it. So it's still implicit differentiation. Continue. And we'll cover log differentiation soon, where we're going to derive the formula for the derivative of a to the u. We had an example where I wanted you to find y prime. And it was x squared plus y to the 7th minus 2y equals 3. Which, by the way, I told you that in this particular equation, it was impossible for us to actually solve for y. So we couldn't actually do this explicitly, even if we wanted to. So implicit differentiation was kind of our only choice here. So let's actually just go over it, because technically I tested you on this kind of thing today. So let's see if we all know how to actually approach it. So we actually did this, but don't look back in your notes. Just like, let's try to actually figure out how to do this again. So what was the first step? What did we do? How do you approach this problem? Yeah?
Like you can sum rule to differentiate each part separately.
Okay, so you're going to go through and differentiate each term separately. So let's see if we remember how to do this. Derivative of x squared.
2x.
Derivative of y to the 7th.
6.
Times y prime. Remember, that's because of the chain rule, because this y is really some function of x that we don't really know what it is. In fact, in this case, we can't even solve for it, right? So it's like, when you see y to the 7th, you're really thinking of this as there's some function raised to the 7th, so you need the chain rule because there's an inside function. Okay, so every time you differentiate a y, which is multiplied by y prime because the chain rule applies, and so the derivative of 2y?
2y prime.
2y prime, whatever derivative of y is, 3 becomes?
0.
0. Derivative of 3 would be 0. Okay, and so now we need to solve for y prime, because that's what we want to find, so that's here. So the goal is to now isolate y prime, so you bring everything that doesn't have y prime to the other side, so we can subtract that 2x. And that will get rid of this guy. Now in the remainder, y prime is a common term, so we can factor that out and be left with 7y to the 6th minus 2. And so we can solve for y prime, and that will give us minus 2x over 7y to the 6th minus 2. So we actually did this last time, and we sort of stopped there. And one concern that I raised, but we didn't really get to it yet, is if we don't even know how to find y in the first place, how is it that having an answer with y's in it can be useful? It can be useful. Here's one example. So we're continuing with the same problem, and the question now is to find the equation of the tangent line. To the curve, this curve. At the point 2, 1. You'll notice that 2, 1 is actually on this guy, because if I plug in x equals 2, that'll give me 4. Move 4 to the other side, I get minus 1. If I plug in 1 and 1 here, that will actually work. So while I don't know how to find the formula in general, I can figure out points on this curve. And this in general can be done. So while solving for y here is impossible, I don't mean it's difficult, I don't mean it will take a long time, I mean it's impossible, right? Doesn't matter how much technology you have, you would not be able to solve for y here. But you will be able to figure out points that are on this graph. You just plug in an x value of interest, and you can kind of solve for the y value and sort of approximate it. And a computer can do that very well. So while it can't solve for the function in general, finding points on the curve or points that are approximately on the curve is actually something that's very doable. And there are algorithms for doing this. So that's why having the answer in y is still useful, because you can use it on a point-by-point basis. Okay, and here you're given a point, so now we're actually going to use this. Yeah?
Why can't you solve that for y?
Because it's a 7-degree polynomial, and there's a math theorem that says there is no general formula for any polynomial of higher than degree 5. So it's like it's sort of something that you have to kind of get lucky with. It has to have some sort of pattern that you can take advantage of. This one happens to not have that pattern, or any such pattern. So that's a much higher level of math than calculus. So I won't be able to justify that to you just now. You would prove something like that in a class called abstract algebra, where you study Galois theory. Yeah. So anyway, so we can actually solve for this, and you can mathematically prove that you can actually solve for it, for the y in that case. But it's still a useful thing to be able to find the derivative. And here's one situation. Okay. So how would we go about finding the tangent line? What do we do when we want to find the tangent line? Yeah.
Plug in the numbers on the y prime formula.
Okay, and what would that give us?
-4/5.
The slope. So I know for a line I need a slope and a point, right? The slope, if it's going to be a tangent line, I know that the slope is given by the derivative at the point. This is a formula for the derivative at the point. So in order to find my slope, I'm simply going to take y prime and I'm going to plug in the values 2 and 1, right? So that's going to be what? Plug in 2 for x, and is that right? Oh, that's that's coming down to like serious rate. Okay, and plug in 1 for y. So we end up with the number -4/5. So that is our slope of the tangent line. And so now we can do y minus y1 equals mx minus x1. And so this would give us y minus 1 equals -4/5 x minus 2. And that would be the equation of the tangent line. So last time we looked at this guy, I told you that the graph looked something like this. And if we plugged in something like 2, 1, that would be, let's say it's over here. That's 2, 1. What we just did was we found the equation of the tangent line at that point. Now, one reason why that's useful is because, again, this function is very difficult to work with in general, but a straight line, we know everything about a straight line. We can work with straight lines till kingdom come. So basically, if we zoom in, the point of a tangent line is that when we zoom in, the tangent line and the function do sort of the same thing. And so working with this is pretty much just as good as working with this, right? So being able to find a tangent line at a certain point. So if there's a function that is particularly kind of difficult to deal with, like you don't even know what it is, what you can do is on a point-by-point basis, you can do calculus. You can figure out slopes at any point, and a computer can help you do that. And you can figure out a tangent line. So at any point that you care about examining this function, you can just make a tangent line there, and instead of examining the function itself, examine the tangent line. Because the farther you zoom in, the better the approximation of the tangent. So that helps us greatly simplify matters. And there are many functions that sort of arise in nature that are very difficult. One thing that you guys might care about is, when you look at something like a financial chart, it's hard to pick a function that would describe you charting a stock, But what you do is you can actually use calculus to approximate what you expect that chart to do. You can make decisions based on that. Let's do a couple more examples just to make sure that we have this implicit differentiation thing down. Again, find y prime is the goal. To log differentiation here, so let's just kind of get through this. Okay, find y prime. How do we do it? So what's the first step? Yeah?
Change 4x squared into ax.
Okay, so we're going to differentiate both sides of the equation. We do that one at a time. So 4x squared, differentiate that, you get 8x. What about this guy?
Distribute 2xy down.
How do we deal with this guy?
2 times
Product.
x.
You need the product rule, right? So you mentioned, because there are two functions multiplying. Remember, your y is a function that we don't know, right? All the derivative rules still apply, so product rule, quotient rule, chain rule, those are all still in effect. So when you see 2x times y, you're thinking that as two functions multiplying by each other, you need the product rule. So I differentiate the 2x, leave the y, plus, now I leave the 2x, differentiate the y. So I apply product rule. Product rule. For the 2xy term. Minus, again, you sort of have the same situation here. I have 3x squared, which is one function, y squared is another function. These are two functions being multiplied. I need to apply the product rule. So the 3x squared is one function. Differentiate that, leave the y squared. So that's going to give us 6xy squared. Plus now you're going to differentiate the y squared, leave the 3x squared. So that's going to give you 6x squared y times y prime, multiplied by y prime because of the chain. That's a negative sign because there's a negative sign in front of it. It's distributed in the product rule. Derivative of 4 is 0. Derivative of 7 is 0. Derivative of ln x is, so it's minus 1 over x. And again, here, I did the product rule for the minus 3x squared y squared. Let's move over here. So we need to find y prime, so we want to isolate the y prime, so identify all the terms that have y primes in them. And you sort of want to get rid of everyone else by moving them to the other side. So on the right side, I already have my minus 1 over x.
I have a question about the product rule used on 3x squared y squared.
Yeah.
So, shouldn't that be y prime times 3x squared because you never derivative, or would you separate it using take the derivative of negative 3x squared the second time?
No, in the first case, I took the derivative of 3x squared, that gave me 6x.
Yeah.
In the second case, when I took the derivative of y squared, that gives me 2y y prime. That 2 multiplied that 3
Oh,
to
okay.
make the other 6.
Okay. That makes sense.
Yeah. So now I'm going to move over the 8x. That's minus 8x. Move over that 2y minus 2y. Move over the 6xy squared, that's plus 6xy squared. That's all that's left. On the left side, I have y prime as a common term, and it's multiplied by 2x. And minus 6x squared. X squared y. And that accounts for it. So now my y prime will just be minus 1x minus 8x minus 2y plus 6xy squared over approximately 6x squared. Other questions on that? Do another example. So e to the x plus y squared, that's all in the power, plus ln of x plus y, again equals 3. How do we do that? Well, I want to differentiate term by term again. How do I differentiate this guy? Yeah?
Take the derivative of x plus y squared,
Uh-huh.
and then you multiply that by 8 to the x plus y squared.
Right, so we know that the derivative of e to anything is just the derivative of the power times the original function. So that's the rule that we're looking at. So once I want to differentiate e to anything, I'm going to take the derivative of the power and multiply by the original function. So that's going to be this guy. Right? So that's why the rules are very important for you to know, and you want to see them as templates. So you can sort of fit this rule on top of this guy, and that's your u. So I want to take u prime times e to the u. So what's the derivative of x plus y squared?
Two y.
1 plus
2y by 3.
plus, now we move on to the next term. ln of x plus y. How do I take the derivative of that? Yeah? U prime over u. So here we're taking the derivative of ln of anything is just the derivative thing over the thing itself. U prime over u. So now this is like my u. That rule will fit on top of this template. So I'm going to take its derivative and divide by itself. Obviously the derivative of 3 is 0. What's the derivative of x plus y? 1 plus y prime. And so now the goal is to solve for y prime. Here we have one of our y primes stuck inside parentheses, so I probably want to get that out, so I'm going to distribute here. So this would mean that e to the x plus y squared, because that's times 1, plus 2y y prime e to the x plus y squared, times that. Plus, let's split this up, 1 over x plus y, plus y prime over x plus y, equals 0. So now I have two terms with my y prime in it. Bring everyone else to the other side. So I would have minus e to the x plus y squared, that's rid of this guy, minus 1 over x plus y, that's rid of that guy. On this side, I would have y prime times 2y e to the x plus y squared, get rid of this term, plus 1 over x plus y. that's and up here. I mean, sure, that's kind of ugly. It's a complex fraction, but you could easily simplify that by multiplying by x plus y over x plus y if you wanted to, and then that would just give you so a little nicer. Either one is excellent. So again, you just go through and do all your derivative rules. You just need to remember when you're differentiating the y term, you have to multiply by y prime because of the change. So the derivative of e to the u applies here, derivative of ln u applies here, product rule, quotient rule, all those things, they're still in effect. It's just that you're applying the chain rule while doing all this. At this point, we won't get a lot of examples on log differentiation, but just before we move on, here's something to try on your own. Something like this might show up on the next quiz or the test, I don't know. But, now, this is an actual equation that comes, I don't know if I want to say in nature, but it's something that was derived scientifically, empirically, by this guy named van der Waals. It's called van der Waals equation. Do any of you do chemistry, or do you have to do chemistry? So, well, this is a fact from chemistry. It's science, and it turns out that this relationship is true. P is the pressure of the gas, and V is the volume of the gas. So it's not like we're just implicit differentiation is some sort of hypothetical situation that we can end up in. No, actual real relationships that you do between quantities can show up, and they can show up in an implicit form. Here you can't really say pressure is just a function of volume or volume is just a function of pressure. They kind of come commingled together. That's how the law came up from experimentation. So this equation holds. And we might want to examine this equation in all sorts of ways. So for example, you can try to find dV dP. In other words, how does the volume change as I change the pressure? Right? How you would answer that question is to find this derivative. You can also find the opposite, dP dV. How does the pressure change as I change the volume? All right, so if my volume increases by 1 atmosphere, how much will my pressure increase? That's the sort of question you can answer using calculus. So I won't actually do that. Try that on your own, see if you really understand implicit differentiation. But for now, I kind of want to just introduce log differentiation. Let's start with some questions that were on the bonus. What is the derivative of A, not E, A to the u, or x to the x. What did you guys write down? What did you guess the answer was? Yeah?
I said u prime times au ln.
Yeah, that's the correct formula for that one. Did you get x to the x?
I don't know. I think I got it wrong, but I think it's x to the x ln x plus 1.
Well, that's what you got too? Okay. So how you'd answer these here is you would need log differentiation. I mean, you don't need it. There are other ways to get to these answers, but you will need log differentiation. So just because you see something raised to a power doesn't mean the power rule applies. Like, it would be wrong, so I should probably point that out. It would be wrong to apply power rule, for example. So if you did something like, oh, the derivative of a to the u is you bring the u down and you subtract 1 from the, yeah, that's right. You couldn't do the power rule. The power rule would not apply. Can you guys see why the power rule would not apply? Huh? Because the base is a constant. In the power rule, if you look at the power rule, the base is a variable and the power is a constant. Here you have literally the opposite. The base is the constant and the power is the variable, which means as a template, the power rule it won't fit. So these rules that you're memorizing, you can also think of them as sort of templates. Like, these are the kinds of problems we know how to solve, and when something is in this position, this is how you find the derivative. So the positions of the constant and the variable actually switch on you here, and so the power rule, it's not effective anymore. We need some other kind of rule. So let's talk about log differentiation. I'll give you the steps, and I'll probably just derive this for you. But one, this is if you're given some function, y equals f of x. Find y prime. And there'll be a couple of situations where you want to use log differentiation. You don't always do it, but in the event that you need to do it, and I'll tell you when these events are, there are really two main cases. Take log of both sides. And simplify. 2, you're going to differentiate implicitly with respect to x. 3, solve for y prime. Now this is actually the process I used to derive the power rule for you. Let's say as an example, let's say my y was a to the x and I want to find y prime. Looking at that, I realize that no rule I have currently applies to that situation, because the power is a variable, and I don't know how to deal with a variable in the power. There's no rule that we have so far for a variable in the power. So the trick is, let's try to get rid of that power. And you ask, how do we get rid of powers? Logs is how we get rid of powers. Logs can turn powers into multiples. So step 1 of what I would do is I would ln both sides, and then I would simplify. The log will allow me to simplify this side. That x I can take down and flip. Now I can actually differentiate both sides implicitly. What's the derivative of ln y? Y prime over y. Right, derivative of ln of anything is just derivative of the thing itself. What's the derivative of x ln a? Yeah?
ln a plus x over, or x times a prime over a.
A is a constant here,
Oh,
which means ln A is a constant. So we're taking x times a constant. Let's derive x times a constant. Yeah, if you have a constant times a function, the derivative just the constant times the derivative of the function, which is just 1. So that's just ln A. Derivative x times a constant is just a constant. So that's our, we've done implicit differentiation, so now we just solve for y prime. This would mean that y prime is equal to y times ln A. But my y was actually a to the x. So that means the derivative of a to the x is a to the x ln A. Which means by the chain rule, if I put an inside function here, I would get that the derivative of a to the u is you differentiate the outer function, multiply by the derivative of the inside function. And that's the chain. So that's the general formula for this. And we use log differentiation to figure that out. We'll stop there. Next time I'll talk about when you want to use log differentiation, but that's one method. And that's how we can derive this one. Which means at this point you now know how to do homework 3.4. I think I didn't collect that last time, but this is the rule that you need to do 3.4. So that's due next time, and we'll talk more about log differentiation. Yeah, we're not. So